we physicists have held up for 100 years, beginning around 1916, for this photograph. It is a region where black holes might just be one of the most fascinating and mysterious phenomena known to mankind. They are massive beasts in terms of power but largely unknown to us. A black hole with a mass 2 to 4 million times that of the Sun might be one of these. Thanks to the research conducted over the past decades, we have gone from knowing almost nothing about them to understanding more, step by step, up close and personal. Things have certainly gotten more exciting. Kaku has declared that we have finally managed to observe the inside out of a black hole. This new information sheds light on details that science might have missed from the start. Join us as we dive deeper into black holes and uncover what's inside. What are black holes? Space is vast, but what exactly are black holes? Before we delve into the details of what Kaku discovered, we need to understand the basics. Most of us have a general idea of what black holes are, but there are still gaps in our understanding. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the idea was purely theoretical. It took another 50 years for scientists to find evidence of their existence, which occurred during the 1960s. Researchers studying the Cygnus constellation observed an unusually bright blue star emitting X-rays. This star wasn't old. It was orbiting a massive dark object. Upon further investigation, it was revealed that the X-rays were being sucked into this object. Thus, the term black hole was coined. This discovery was groundbreaking because it proved that black holes were not just figments of Einstein's imagination but real entities in space that required further study. Scientists around the world began focusing on this black hole, named Cygnus X1, located in the Cygnus constellation roughly 6,000 light-years from Earth. It was 10 times brighter than the Sun and incredibly dense, with such a strong gravitational pull that not even light could escape it. For this reason, it was called a black hole. The nature of black holes. The concept of a black hole is both fascinating and terrifying, a region of space where gravity is so strong that nothing, not even light, can escape. Anything that ventures too close to a black hole is inevitably pulled in, never to be seen again. This danger makes it even more crucial to learn all we can about them. After discovering Cygnus X1, scientists began searching for other black holes and found that there may be over 100 million black holes in the Milky Way alone. Since they are incredibly difficult to detect, we still don't have an exact count. Nonetheless, there appear to be several million black holes in our universe, making them even more critical to study. The primary concern with black holes is their immense gravitational pull. Their gravity is so powerful that anything entering them is compressed infinitely until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners, pulling in everything in their vicinity. One of the most terrifying aspects of black hole research is that if someone were to fall into one, they would be stretched into a single line. This process would occur gradually, and the individual would die long before reaching the singularity. Are black holes a threat to us? Fortunately, no. The nearest black hole is about 500 light-years away, which is far enough not to pose a direct threat. In 2021, researchers managed to capture the first clear photograph of a black hole, specifically the M87 black hole. This black hole was observed over several nights. The scientists pieced together multiple images to create a complete picture, revealing that black holes have 3 layers. Contrary to popular belief, a black hole isn't just a single gaping void. The first layer is the event horizon, the point of no return. Once you pass this point, there's no turning back. You're inevitably pulled into the black hole. The second layer is the photon sphere, where light orbits the black hole. Any light entering this region is trapped and cannot escape the gravitational pull. Finally, we reach the third layer, the singularity. This is the core of the black hole, where everything entering is compressed into a point. At the singularity, the laws of physics as we know them break down, and we cannot predict what happens next. Challenges of studying black holes. Every black hole studied so far has been unique. While they generally follow the same 3-layer concept, their specific behaviors can vary significantly. Studying these singularities typically involves looking through telescopes and observing indirectly. Sending a probe, such as Voyager, into a black hole is impossible. Anything that enters the event horizon is pulled toward the singularity and compressed to an infinitely small point. As a result, scientists cannot afford to waste billions of dollars on probes that would be destroyed. Instead, researchers study black holes in a two-dimensional way, despite their three-dimensional nature. This makes the study of black holes immensely challenging. To complicate matters further, each black hole is different, and the laws of physics break down when analyzing their interiors. This means standard methods of scientific inquiry don't apply to black hole research. Anyway, researchers haven't been idle. There is a seriously huge number of speculations and explanations about black holes. One persuasive theory is that they are formed from collapsing stars. Exactly when a star exhausts most of its fuel, it can no longer produce adequate energy to counteract gravity, causing it to collapse in on itself and potentially become a singularity. To understand the nature of black holes in detail, NASA researchers focused their attention on the center of the galaxy M87. Astronomers observed a strong flow of extremely hot hydrogen gas spinning at an astonishing speed of 1.2 million miles per hour. The sheer force of the spinning disk of gas should have caused it to fly apart, yet it didn't. Scientists theorized that a massive object at the center of the galaxy prevented this. This colossal object, weighing as much as 2 to 3 billion suns, could be a black hole. However, that isn't the only theory. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe a rotating black hole, suggesting that it wouldn't collapse into a point but would instead form a ring of fire or a thin circle. This spinning disk of matter, called the ergosphere, is the region surrounding the black hole where the laws of physics start to break down. Kerr's equation also predicted the existence of an Einstein-Rosen bridge, or wormhole, a hypothetical passage through spacetime that connects two separate regions of the universe, or even two parallel universes. If one were to fall into a black hole rather than being crushed, they might be sucked down an entry through the ring of fire and ejected out of a white hole in a parallel universe. To understand how this works, consider the concept of spacetime in Einstein's theory. Existence is interconnected, forming a four-dimensional surface called spacetime. Objects with mass distort this surface, creating a gravitational field that makes other objects move toward them. Imagine a piece of paper representing spacetime. If you place 2 points on the paper and draw a line between them, it represents how objects travel through spacetime. If you fold the paper in half to create a shortcut between the 2 points, this represents a wormhole, a shortcut through spacetime that connects two distant points instantly. Wormholes aren't just a sci-fi concept. They are a prediction of general relativity. However, no one has observed one directly. Wormholes are inherently unstable and would collapse quickly. The existence of an Einstein-Rosen bridge would mean black holes are not just cosmic vacuum cleaners but could also serve as gateways to other regions of spacetime. Could we use a wormhole to travel through space and time? Unfortunately, the answer is likely no. Not yet. Even if we could stabilize a wormhole, it's unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is the ultimate limit for how fast anything can move through spacetime. Despite this, the idea of wormholes and black holes as pathways to other parts of the universe or different times has fascinated physicists for decades. The possibility of shortcuts through spacetime, allowing for crossing vast distances or traveling into the past, could be revolutionary if achievable. The Kerr wormhole, named after Roy Kerr, is one of the most intriguing ideas in this field. A theoretical passage through spacetime might connect two far-off points, such as different universes or different times within the same universe. The hybrid wormhole, which is ring-shaped like the mirror in Alice in Wonderland, could potentially transport a traveler to another universe or time with different physical laws. While the idea of wormholes as means of interstellar or time travel is exciting, it is also controversial. Some physicists argue that wormholes, particularly Kerr wormholes, might be unstable or impossible to traverse due to extreme radiation and subatomic forces. Critics point out that Einstein's equations, used to describe wormholes and black holes, work for gravity but not for the quantum forces that govern radiation and subatomic particles. To truly understand these phenomena, a new theory is needed, one that unifies gravity with quantum theory. A theory of everything. Michio Kaku, a renowned theoretical physicist, has been working on such a theory for decades. The leading candidate is string theory, which unifies gravity with quantum mechanics. It suggests that subatomic particles are tiny vibrating strings and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. String theory also explains various strange phenomena by showing that, as strings move through time, they warp the fabric of space, creating black holes, wormholes, and other exotic solutions to Einstein's equations. However, the extra dimensions of spacetime predicted by string theory are so small that we cannot study them directly. Most experiments only involve the 4 dimensions we know: length, width, height, and time. How can we know the extra dimensions exist? One possibility is that these dimensions are curled up tightly, making them invisible to us, like a sheet of paper rolled into a cylinder. Another possibility is that these extra dimensions were more apparent at the universe's beginning during the Big Bang. According to some interpretations of string theory, the universe began in a state of 10-dimensional spacetime, with all dimensions equally visible. As the universe expanded and cooled, the extra dimensions folded away, leaving us with the 4 we observe today. If this is correct, we might detect traces of these extra dimensions around us. The mathematics of string theory is incredibly complex and has opened new areas of research. However, solving the problem of a quantum black hole has proven difficult. Despite many attempts, no one has succeeded yet. Edward Witten of the Institute for Advanced Study at Princeton describes string theory as 21st-century physics that fell by accident into the 20th century. Recently, physicists announced a breakthrough. String theory could solve the problem of a quantum black hole, but only in 2 dimensions, not 10. Many believe it's only a matter of time before someone cracks this problem. Until then, it's too early to expect intergalactic or time-traveling efforts. One thing is clear: there are too many questions and even more potential answers. Michio Kaku's string theory adds another twist. Perhaps the Big Bang wasn't as explosive as we think. It might not have been a massive blast, but rather a collision between universes or the emergence of our universe from another. This connection between universes is known as a wormhole, like a tunnel connecting 2 bubbles. We might have already found evidence of this umbilical cord, linking our universe to another. In a way, we could be living inside a black hole, unaware of it, because we exist in 4 dimensions and can't see beyond them. It's possible that the black holes we study are wormholes to other dimensions.